Hello everyone. In this lecture, we are going to derive the Navier-Stokes equations. So this is kind of the governing momentum equation for viscous flows, and it's kind of the final equation that we are going to derive for the momentum equation. So before I start, I want to remind you what equations we had and we derived so far for fluid flows. And then based on that, we are going to add also the viscous effects that we neglected in previous derivations. So first, a reminder. So first we have continuity equation. So we derived first continuity equation, the differential form of that, of course. So continuity equation was partial rho over partial t plus grad dot rho v equals to 0, or the divergence of velocity is minus 1 over rho d rho dt. So this is the second or alternative form of continuity equation. So this is in vector notation. In index notation, so this is vector notation. So if you want to write this in index notation, or Einstein's index notation, we can write it as follows: partial rho over partial t so partial rho over partial t plus partial rho ui over partial xi equals to 0. Or this equation, the divergence, you can write it as partial u I over partial xi equals to minus 1 rho partial t plus ui partial rho partial xj. Okay. So this is a continuity equation in two notations, one in vector notation and the second one is index notation. And now let me write the momentum equation as well. So momentum equation. So we derive the momentum equation, the partial differential equations of momentum equation for an inviscid flow, which is actually Euler's equation. Okay. So let's see what is this in terms of vector and index notation. So first I write vector notation. So Euler's equation in terms of vector notation is rho dv over dt which is the inertia, equals to minus pressure gradient force plus the gravitational force. So sum of the forces except viscosity, right? So it's a inviscid flow. So rho g, which is a vector. Okay, so now let's go to the index notation of that. So let's see how this is written in index notation. So I'm just gonna divide everything by rho, assuming that rho is constant. So I'm gonna get partial ui over partial t plus uj partial ui over partial xj equals to minus 1 rho partial p over partial xi plus rho gi. Okay, so this is the index notation of Euler's equation or momentum equation for an inviscid flow. Okay, so now let's see let's consider momentum equation for a Newtonian viscous fluid. So now we also has viscosity, and we want to see what term we need to add and what terms we need to consider here. Okay, so we now consider momentum equation for a Newtonian viscous fluid. Okay, so when we have viscosity, I am going to use another way for showing the stress on any fluid particle. Okay, so say you have a fluid particle, okay, any fluid particle, and then say something like this, for example, and then instead of for all the, so we can kind of decompose all the forces into two type of forces for this fluid particle. One is, so say we have this particle, fluid particle. One is body forces, which are due to gravitational forces, and the other one are surface forces. So one volume forces or body forces, and one contact forces. So the contact forces, for the contact forces, for example, this could be any stresses that are kind of applied to this. So it could be shear stress, or it could be pressure, any stress that is kind of applied to that particle. So we could show that and just write it in a general way as a surface stress, okay? So we can write as surface contact forces, okay? And when we want to write that on the right hand side of our equation for the sum of the forces for the momentum equation, we can have surface contact forces plus the body forces which are applied to the volume, okay? So I can just write the sum of all contact forces, say surface contact forces. I can write that as, for all, I can just integrate it for all the fluid particles over the surface of any control surface of any control volume that I have. So say you have any arbitrary control volume, okay? And then you want to take this integral over the control surface of that, that control volume to get all the surface contact forces that are acting on that control volume or on that fluid particle, okay? So then I showed that those forces with T bar those stresses actually was T bar. So this is the contact stress, these are the contact forces. So this is gonna be stresses, the stress vector at any point that is on that, say, particle, right? So you might have, say, a lot of stresses like here, different type of stresses, right, that act here. So we just show this with T at each point on the surface. You could have, necessarily it's not always the same direction, it could have its own direction. So we show those stresses with T, so this is force per area. And then we multiply that by dA, small surface that it's surrounding that. So say if you have here this is gonna be your dA, say, and then you have this T stress there, and then you integrate this over the whole control surface to get the total surface contact forces for that, okay? So there is a theorem which is known as Cauchy stress theorem that states that in this kind of, it's a theorem for from continuum mechanics, so I'm not going to go through that. It's a general theorem. But the theorem states that, so according to Cauchy's stress theorem, you can relate this stress vector at any point by defining a stress tensor. So you may define a stress tensor sigma, and then you can represent this Tn stress on the body of any, on the surface of the object, any object, with and the normal vector dot a stress tensor. And I'm going to go through what is a stress tensor here, okay? So you can find these stress tensor, and it's actually in the principal. You can bring all the stresses into the principal axis in three principal axes. So I'm not going to go through that how you can do it, but this is a general theorem that states that you can write these stresses, surface contact stresses, using these stress tensor, or like it's kind of and I'm going through what is this sigma and what does this mean. And this is just a theorem, and you can prove that it can be written as this, as a stress tensor. But I'm going to use this theorem to kind of simplify our work, because then the F of all, say, surface forces become the integral over the control surface of, I just gonna replace this n dot sigma stress tensor. So this is a stress tensor. So I'm going to replace that with this. And then what I'm going to do, I am going to use the divergence theorem. So you put this in the integral form, right? If we have this, say, if we have the momentum equation in the integral form, and then we want to derive the momentum equation in differential form, what we did is we convert every surface integrals into volume integrals, right? So I'm going to use the same technique here. So for all the surface or surface forces, which equals n dot sigma dA. So I'm using I want to use the divergence theorem. So divergence theorem that we use in deriving Euler's equation and the differential form of Euler's equation. So this is going to convert this area integral to a volume integral. So over the CV, over the control volume, by grad dot sigma dV. Okay. So now this will go, because this is the sum of the forces, contact forces, this will go to the right hand side of our equation. So in general, the linear momentum equation with a general stress tensor can be written as so let's look at this one. So let me first write it in the vector notation. So the left hand side is the same. So what's gonna differ now is the right hand side, the sum of the forces. So I still have this rho g, but now I have a general form of stress forces, which can include both shear stress and pressure forces. These are surface contact forces, right? So again, it's going to be the sum of the forces. So the left hand side is like, again, MA equals to sum of the forces, right? This is the momentum equation, linear momentum equation. So we have it on the left hand side. So MA is just mdv over dt, right? So this is just, again, the Newton's second law and some of the forces. So the forces that I have are contact forces. So it's going to be these forces and plus the body forces, which was gravitational force, right? So this is the only contact forces. And again, if you look at this, this is in the integral form, and in the differential form, you will just bring this out of the integral, because this was, if you remember, we did that trick and we wrote everything in terms of the control volume and volume integrals. So I can write this as grad dot sigma plus, so this is the contact forces or surface forces, plus the body forces here, which is going to be just gravitational force, which is rho g. Okay. Or in terms of the vector index notation, so in index notation, this is going to be, again, I'm going to divide everything by rho, so it's going to be partial ui partial t plus uj partial ui over partial xj equals to 1 rho of partial sigma ij. This is a tensor, and I'm going to talk about this, what this means, partial xj plus rho gi. Okay. So this is now a more general form than the Euler's equation, because it also accounts for all the surface stresses, not only the pressure, but also the viscous forces or shear stresses that are acting on any fluid particle. So now let's see what is Cauchy stress tensor, or in general, what is stress tensor? So we can write the stress tensor as this. So let's look at one fluid particle. So let's assume we have a fluid particle here. Okay, so this fluid particle, and then we have 3 axes here. Okay. This is x2. So we name these axes. This is x1, this is x2, and then this is x3. Okay. So this stress tensor we define it as follows. So this sigma ij. So I component is going to show the phase, which phase we are in, and J component is going to show the direction of the stress. So let's see, what do I mean by this? So say we are in this phase, okay? And we want to show the stresses here on this phase that act on this plane. So the first stress is, let's say, stress that is just perpendicular to this phase and parallel to axis x1. So if I want to say this is in phase 1, right? So I'm going to show it this 1, and also it has the direction of 1 because it goes to x1. So let's go to the other one. So let's say this is stress. So again, this is in phase 1. This is phase 1, right? Let me show it here, write it down so you better understand. So this is phase 1, this is phase 2, and this is phase 3. Okay, so now we are in phase 1, but now the stress vector is toward axis 3, so this is going to be sigma 1 it should be sigma 1 3, right? So based on this, we can just write all the stress vectors, and this will give us a stress tensor. So let's see what we have. So this is going to be sigma 1 3, and then this one is going to be sigma 1 2. Similarly here, so this is going to give me sigma 2 2. This is sigma 2 3, and this one is sigma 2 1. Here, this is going to be sigma 3 2. This is going to be sigma 3 1. This one is going to be sigma 3 3. Okay, so this is going to give us all the stress terms, and this is the stress tensor here. So in general, I can write it as this matrix, this stress tensor, I can write it as this matrix, sigma ij equals to this matrix, a 3 by 3 matrix, sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 2, sigma 2 3, sigma 3 1, sigma 3 2, sigma 3 3. So this row shows all stresses acting on a fluid particles phase 1, right? The second row shows all the stresses that act on the fluid particles phase 2, and similarly the last row. And this column, so this column shows the direction of the forces. So the first columns are all the stresses that act on the direction 1, x1, second column direction 2, and third column direction 3. Okay, So the equilibrium of infinitesimally small volume stresses states. So if you have very, very small volume of a fluid particle, then all these stresses have to be in equilibrium, right? Otherwise, the particle is gonna tear down, right? So it's gonna deform and distort completely. So, but you can reach to a very, very small volume that particle is never gonna change its shape. Okay, so in that state we have kind of a equilibrium of all the stresses. So based on that equilibrium, we can write that sigma 2,1 should equal to sigma 1,2. What does this mean here? This means that these two terms this stress should equal to this stress because they are in equilibrium. Otherwise, you will have some kind of distortion. Okay. Similarly, sigma 2,3 should equal to sigma 3,2, and so on and so forth, or sigma ij should equal to sigma ji. Similarly, sigma 2,3 should equal to sigma 3,2, or in general, we can write sigma ij should equal to sigma ji. So this means that sigma ij is symmetric. So this means that it only has 6 independent components of stress tensor. Meaning this one equals to this one equals to this one, and this one equals to this one. So the only independent components are this part of the matrix. These components are all independent. Okay? So we call sigma ij is a second order symmetric tensor. And these tensors have some properties that will kind of simplify our equations. Okay? So in the next session, I'm going to show these stresses in a fluid at rest and also in a fluid at motion. So what would these stresses actually mean when we have a fluid at rest that is not moving and also a fluid that is actually moving? So this was a general form of momentum equation, and this is the stress tensor, that how we kind of describe all these surface forces on the fluid particle.